All right, good morning, everyone. Happy Friday. We are about to set off into the fourth unit of the class, which is stability. At this point, it's prudent to just pause and take a look back and see what we've done so far and maybe get a preview of where we're going. So we started with a week-long unit on how to model a system, basically a crash course in taking the physics that you learned in your first and second years and transforming those into mathematical descriptions of physical systems. And then that led us to discussion of differential equations and Laplace transform of those, and therefore transfer functions. If each subsystem has a transfer function, we studied ways to combine systems and reduce them to make several subsystems into one larger system with a transfer function. And so once we had a reasonable way of modeling complicated systems as a single transfer function, then we started talking about how can we analyze those systems? The first procedure of which was to analyze the transient response of the systems. So we learned about different metrics that you can apply to the transient response, usually to a step response. So those were things like overshoot percentage, rise time, peak time, and settling time. If the system happens to be second order and underdamped and stable, then we have these nice handy shortcuts to go from the transfer function straight to the step response metrics. At the end of that, we took a step back and said, well, why are we spending all this time on second order systems? And the answer is, it's because we can. And also, higher order systems can sometimes be approximated by second order systems, or I guess just lower order systems. Then we had a 2-day unit on steady state performance, and that all came down to steady state error. There were two main thrusts there, that there is steady state error due to the reference input. That is, sometimes your system just can't reach where the reference input goes, and we called that steady state error due to the reference. And the other thrust was you can have error due to a disturbance. And there the key insight was any output due to a disturbance input is error, because by its very nature, a disturbance input is something you don't want the system to do. So anything the system does is bad. Okay, and that brings us to the third leg of this kind of system analysis table. We had transient response, we had steady state response, and now we're going to talk about stability. So these are the three main, I call them the legs of the control table, that if you're going to design a control system, you have to have all three meet the requirements in order to say that you've done your job. So that was a 3-minute crash course on the last 3 weeks. Any questions? All right, join me on the PowerPoint slides and away we go. All right, so we are going to talk about stability today. And at least when I teach 228, I talk about two different classes of stability. And these, again, these are system classes, not signal classes. So when I teach 228, I talk about external stability versus internal stability. It's been brought to my attention that many of the other instructors of 228 focus only on external stability. Has that been your experience? Bounded inputs, bounded outputs, that kind of business?
Yeah.
Okay. So just to recap, external stability has to do with if something is applied externally to the system, does the system go crazy or not? Now, the caveat that we're going to put on that is that the only thing that we're allowed to put in this notion are not crazy inputs. Therefore, if you put in a not crazy input, you should get a not crazy output. I think that's the layman's interpretation of external stability. There is a consequence of this definition that a system is externally stable if and only if its impulse response is absolutely integrable. So remember, absolutely integrable means when you integrate the absolute value of the impulse response over all time, you get a number that is finite. Internal stability has, as you might expect, to do with the internal workings of the system. That is, an internally stable system will have nice responses in the absence of external stimulation. So that's why we talk about the zero input response when talking about internal stability. So the definition of an internally stable system is that the ZIR due to any set of initial conditions decays to 0. So remember that the ZIR of an LTI system is comprised only of characteristic modes. And these are, of course, characteristic modes, again, are e to the lambda t u of t, where lambda is a characteristic root. Okay, so that's it's also kind of attention that not every 228 instructor talks about what modes are, and modes are just the functions that you get when you take the characteristic roots and you put them in exponents. Okay, so if you want all of your characteristic modes to decay, and that is what you want if you want the ZIR to decay, then that is equivalent to all of the characteristic roots. All of these lambdas are in the left half plane. And then strictly is kind of important here, right? Because if you have modes like e to the plus or minus, I don't know, 3jt, then you're going to have a ZIR component that oscillates forever. And this doesn't blow up, but it also doesn't decay. So it kind of sits right on the edge between good behavior and bad behavior. So when I say strictly in the left half plane, I mean that the real part of all of the lambdas has to be strictly negative. This is a strict inequality because it lacks that equal sign, or the bar down here. So if you have this scenario, and again, characteristic roots and system poles are synonymous. Okay, so I wrote this slide in the verbiage of 228. But in 302, I'm going to pretty much always just call these poles. So if all of your poles are strictly in the left half plane, then all of your characteristic modes are going to decay eventually, which means all of your ZIRs will also decay. Okay, that's how that implication chain works. If any of your poles are on the imaginary axis, then you get oscillatory modes, or you get non-decaying modes. And of course, if anything is in the right half plane, so again, this mode contributes this kind of behavior, which is in no way stable. Okay. So the difference between these two is very slight, and it usually comes in the form of improper transfer functions. But there's this, I want to call your attention to this sentence down at the very bottom, is that if you're talking about what are called proper transfer functions, and again, those are transfer functions whose numerator order is equal to or less than the denominator order, then these two are equivalent. These two classes of stability, if you're one, then you're the other. So again, this is things like transfer functions like b sub I s to the I, where I runs from 0 to m over a sub j s to the j equals 0 to little n. And a proper transfer function is one in which m is less than or equal to n. Technically, a strictly proper transfer function is where this inequality is strict. Okay, but for our purposes, if the transfer function is merely proper, then internal and external stability are the same. Okay. And the reason I bring this up is because the vast majority of like real world systems are proper. They are proper transfer functions. Okay. So I want to take a little bit of time and talk a little bit more about this case where you've got poles on the imaginary axis. And it gets its own name because it lives in this kind of knife's edge between responses that decay and responses that blow up. So it's called marginally stable when the rightmost pole, I guess this is polar poles, is /r on the imaginary axis. So this left-hand system is, we call it marginally stable. And I think this is a misleading term. I would rather, if I mean, no one asked me, but I would say marginally unstable, just to stress that this is usually not a good condition for a system to be in. Now, that's not to say that a lot of times, well, sometimes in electrical engineering, you want to build something that oscillates, right? So an oscillator is actually quite a useful system in EE. And in those systems, you actually do want to put your system poles directly on the imaginary axis. But in the vast majority of electromechanical systems or purely mechanical systems, this is a bad news situation. You want your system to be strictly stable. So I think it's a bit of a misnomer to call these marginally stable, because that gives students the idea that, oh, it's got stable in the name, that must mean it's good. And I want to disabuse you of that. So this is usually a bad situation to find yourself in. But what we've got here on the left is a marginally stable system. This is one who, if you were to observe the response due to any initial condition, you would get what I had on the last slide. You would get this never-ending oscillation. So this would be like the ZIR versus time. I did highlight this is actually a Bibo unstable system. So because there is one bounded input that produces an unbounded output. Can you picture what that input would look like? If I said to you that this is a resonant circuit, then you would say, oh, okay, this is an LC circuit with no resistor. Therefore, if I excite this system at this frequency, call it omega resonant, then what kind of behavior are you going to observe? So here, if I input an omega R sinusoid into this system, what am I going to observe? I'm going to observe resonant growth, so linear growth here. Okay, and this is bounded, and this is unbounded. Okay, so that's why I'm able to say that this is a marginally stable system, but it's Bibo unstable. Now, if these poles were to get nudged just a hair into the left half plane, we no longer get this unbounded behavior. Okay, and everything becomes stable, and everyone's happy. Sorry, I'm happy. Let's contrast the left-hand system with the right-hand system, in which the rightmost poles are on the imaginary axis, except they have what we call multiplicity 2. So these are repeated poles on the imaginary axis, in which case there is actually any initial condition set is going to produce this growing oscillation behavior. Okay, so this is again the ZIR versus time. And just to complete the picture here, this was the ZSR when the input was that resonant sinusoid. Okay, so this is all kinds of unstable. It's both internally unstable and externally unstable. I think a lot of people, when they think of marginally stable, they think of, oh, a system whose rightmost poles are on the imaginary axis. And that's most of the picture. But again, that doesn't cover this scenario that I have on the right-hand side here. This right-hand side pole zero diagram also has its rightmost poles on the imaginary axis, but it is unstable. Was there a question raised?
Yeah, I was going to ask you, is it still considered marginally stable if it doesn't have an imaginary component? Like if you're on the real line?
Ooh, good question. So let's check that out. How can I erase? Let's buy ourselves some room here. So yeah, these pictures all have complex conjugate roots, but so okay, to be on the imaginary axis and also to be real, there's actually exactly one place that happens. Yeah. So I would call this system marginally stable, because if you were to observe the ZIR for this system, it would look like this, which again, it doesn't grow, but it also doesn't shrink. Okay, so, and that's the hallmark of a marginally stable system. However, if we increase the multiplicity of that root at the origin, then what does the ZIR look like? Looks like that. Okay, so actually the same statement applies if your pole is at the origin. A single pole at the origin is fine, but anything more than a single pole at the origin is unstable. Does that answer your question?
Yeah, it does. Thank you.
Yeah, no problem.
I have a question real quick, if I can.
Yeah, please.
When we were doing the error steady state, we found that we liked poles at the on the access, but here we're saying we don't, and I would just like to clarify how these things work together.
Yeah, for sure. So let me ask. I will answer your question, but I want some feedback from you, so to speak. Get it? Feedback. Which poles did we like at the origin in the steady state error? Like, where were they the system poles, the closed loop transfer function poles, or were they a subsystem transfer function?
Oh, subsystem.
Yeah, it was just the forward path transfer function that we liked having integrators in.
Okay.
And I mean, my statement here is valid. That would mean that subsystem is unstable. However, as we will see, next slide, instability of a subsystem does not imply instability of the closed loop system.
Okay.
I think I anticipated your question.
Oh, thank you.
Yeah. So, but that's a great point. Is that learning about stability, you're trying to juxtapose that with your steady state error knowledge, they do tend to butt heads. But let's take a quick look at this statement. So I want to cook up a toy system here, and it is one in which there are two free parameters. There's an open loop gain or numerator k and a pole location a. Okay, unity feedback. It's basically the simplest feedback loop you can imagine. And I want to imagine a couple of cases here. So let's imagine a case when k is either 2 or -2, and cases in which a is either 1 or -1. Okay, so can you see what's going to happen in this table? This is basically 4 system configurations based on what a and k are. So I want to talk about 2 different notions. I want to talk about open loop stability versus closed loop stability. And open loop stability is exactly what it sounds like. It is the stability of the open loop transfer function. So the open loop transfer function is the transfer function that you'd get if you were to break this loop. How can I undo? There. And so it's exactly just k over s plus a. The closed loop transfer function is the overall input to output transfer function, and that would be what I think it's k over s plus a plus k. And this is the biggie right here, is that by changing k, I don't change the pole location of the open loop transfer function, but I certainly change the location of the poles of the closed loop transfer function. Okay, so let's work this out. If k is -2, well, actually, k has no bearing on the open loop stability, right? Because k has no bearing on the open loop pole. And so the open loop stability is entirely dictated by a. So if a is 1, that means the pole is at -1, so this is open loop stable for both of these. And then conversely, it's open loop unstable if a is -1, which means the open loop pole is at +1. Okay, so there is the open loop analysis. Now let's talk about the closed loop stability. The closed loop pole is the s value that makes this denominator 0. So it is always at -a minus k. All right, so this is our closed loop pole location. And so if a and k are both positive, this is certainly a negative number. So this is closed loop stable up here. If a and k are both negative, then this is clearly a positive number. So this is closed loop unstable down here. And the other 2 entries in this table are going to depend heavily on the absolute value of a and k. So here we've got 1 and -2, so that sends a -1. The negative of that is +1, so this is closed loop unstable. And in the bottom right, we get, if we were to add to a -1, we get +1, the negative of which is in the left half plane, so this is closed loop stable. Okay, so this is just a kind of a quick back of the envelope proof that the stability or instability of this subsystem is almost completely decoupled from the stability or instability of the closed loop system as a whole. Right? So there was some arithmetic we had to do to get these two statements. So it's not like you can make any unstable system stable or vice versa. But I don't want you to think that there is any direct correlation between stability or instability of any of the subsystems and stability or instability of the closed loop system. A big part of this class will be determining what kinds of open loop subsystems produce stable closed loop subsystems. So like that's one of the learning outcomes of this course, is to be able to accurately predict what open loop subsystems produce good, stable closed loop systems. But at its face, or at this point, they are independent, they're decoupled. Anything else on this? I think this is an important concept, not like the actual numbers here, but the fact that you can have stable subsystems and unstable closed loop systems and vice versa. This is normally where this is the Spider-Man part of the class, where I say, you as a control engineer have this great ability to stabilize otherwise unstable things, right? This is actually what I'm talking about. We're going to take an open loop unstable system and create a closed loop stable system. This is with great power comes great responsibility, and that is this one. Is if you do your job poorly, you could take something that is nice and stable and you could make it unstable. Okay, so that's my my comic book pitch here. Is you could save the world or you could ruin it. No pressure. I'm just going to assume that you're smiling. Okay. So the math behind all this comes down to, can you find the roots of a polynomial? That in itself is actually a fascinating question. And it has been actually answered, is that if you have a first, second, third, or fourth order polynomial, there are formulas to write the exact location of those roots. Okay. So first order polynomial is not hard. It's like x plus a equals 0. So that's pretty easy. Second order polynomial, you can use the quadratic formula. For a third order polynomial, there is what's called a cubic formula, but it's pretty hairy. And for a fourth order polynomial, there is what's called a quartic formula, and it is obscenely difficult to write. So I want to say that for practical purposes, for back of the envelope calculations, there are reasonable formulas for first and second order polynomials. For stranded on a desert island with nothing better to do, there are formulas for finding the root locations of third and fourth order polynomials, but that's where the story ends, because it's actually been mathematically proven that there are fifth order polynomials out there for which it is impossible to write a closed form expression for the root locations. And that, I think, it surprises me, is something that there's some magic change between a fourth and a fifth order polynomial, that every fourth order you can write out, like if you had enough time, you can write out the locations of the roots. But as soon as you go to fifth and above, there are combinations of coefficients for fifth order polynomials that make it impossible to write the root locations. So what does that mean for us as engineers? Well, for us as engineers, we're alwast always going to be making numerical approximations. So if you have anything from a third order on up, no one would bat an eye that you're going to use what's called a root solver or a root finder, which is an algorithm to find the roots of high order polynomials. And so, yeah, this bullet point might scare you, and it might make you think that you can't find the roots. I don't want you to come away with that impression. You can approximate the roots to an arbitrarily good degree, which for engineers is often all you need. But I think it's a fascinating mathematical fact that you can't write the exact location, right? This is the difference between saying the root is at the root location is at 2, or the root location is at the square root of 4, versus my numerical approximation approximates the roots to be at 2.000000001. Okay. Right, for engineers, as long as you take as many zeros out as you need and you are able to do that, that's often good enough. So why are we going to spend any time at this if analyzing system stability is the same as just plopping it into a root finder algorithm? And that's because analyzing a system stability is pretty darn easy, right? It's exactly what I just said. If the system is linear and time invariant, then you just plop the denominator, the denominator of the transfer function into a root finder and your job is done. Designing for stability is a significantly harder process, right? Designing for stability means that the coefficients of your denominator of your transfer function aren't set in stone. They aren't finite numbers. They aren't fixed numbers. They are variables. And plopping in a variable into a root finder is a vastly different algorithm. So let me give you another picture about what I'm talking about here. So let's say that we have a process that we'd like to control. And the proposed controller is some kind of low-pass filter, first-order low-pass filter. We don't know K and we don't know A, but we'd like to design K and A such that the closed-loop system is stable. Like let's say that's our only design goal. So what are we going to do? We're going to let the process transfer function have some numerator and some denominator. If you wanted to spice things up a bit, you could say the denominator has some right half plane roots. That would be interesting. This is then an unstable process that we're going to try to stabilize. The closed loop transfer function is what? It's K, S plus A, times the process, that's an N, sorry, over 1 plus that same quantity, because we're doing unity feedback. Okay, so multiply top and bottom by S plus A times D of S, and we get K, N of S on top, S plus A, D of S, plus K, N of S. So this is where I'm saying that designing for stability is significantly harder, because A and K now appear on virtually every coefficient in this denominator, right? And A and K are unknowns. So you think to yourself, well, I could do a for loop, right? I could do for A equals 0, I don't know, to your favorite number. And then within that for loop, K equals 0 to your second favorite number. And then you could test what are the roots of the closed loop characteristic polynomial as a function of A and K. Right, this is, I hope you see this is pseudocode. Don't try and actually implement this. But I mean, that's fine, but it also means that the runtime of this search script is going to depend on your discretization factor. So are you stepping by ones? Are you stepping by 0.1s? Are you stepping by 10s? Your choice there in how to step from 0 to 10 or 0 to 100 affects the runtime here. And also, I mean, who's to say that 0 is a good start point? Who's to say that 10 or 100 is a good endpoint? So yes, you could use a computer to, and the reason I'm putting this into a for loop is because this roots command is a MATLAB command, and it will find the roots of, it will approximate the roots of an arbitrary polynomial that you give it. What I'm trying to say is that with A and K as variables, this polynomial cannot be directly plopped into a root finding script, a root finding algorithm, because that root finding algorithm will expect fixed numbers for all the coefficients. Okay, so I'm trying to outline, on one hand, this problem is dead simple. When all the coefficients are fixed numbers, there's really nothing to do here except use a calculator. On the other hand, when any of the coefficients are variables, this becomes virtually intractable. Okay, so I'm trying to set up this this juxtaposition in your minds to basically justify the rest of the content of this unit. So, questions on this dichotomy between super easy and seemingly impossible? So enter what's called the Routh-Hurwitz Stability Criterion. And so what Routh-Hurwitz says, or what Routh-Hurwitz promises, is the ability to tell you, given any polynomial, including a polynomial with variable coefficients, how many roots of that polynomial are in the right half plane. Now you might think that that seems to directly contradict my statement from a couple slides ago, which says that you can't find the root locations of a fifth order polynomial in general. And I want to highlight the fact that this is not saying that. This is only promising you the number of right half plane roots, not their locations. Okay, so this is only going to tell you how many of the roots of a polynomial in the right half plane and how many in the left half plane, not where exactly in the right half plane those roots are. Okay, so this is a trade-off. We are going to give up some specificity. That is, we're not going to ask where the exact locations are, but in exchange for that trade, we are going to be able to say, are there any in the right half plane? And that's really what it comes down to for engineers. We are mostly concerned with, is this 0 or not 0? Right, Routh-Hurwitz promises a little bit more, and Routh-Hurwitz can be used for a little bit more, but for engineers, this is the primary question. Is there anything in the right half plane or not? Taking that one step further, using the Routh-Hurwitz criterion on polynomials with variable coefficients, we can say what range of those coefficients, so 0 less than k max, will imply 0 right half plane roots. So that's going to be one of the things that Routh-Hurwitz enables us to do. And this is something that you could approximate with that for loop that I was talking about on the previous slide, but the Routh-Hurwitz actually will give you a precise value for k max here. Okay. So questions on why this is not promising something that can't be delivered? I think that's a common question the students have. Is I just say you can't do this for fifth order polynomials, and then 10 minutes later I say let's do this for any polynomial. But the key is I'm only going to tell you how many are on the right, how many on the left, not where they are on the right or where they are on the left. That's the trade-off here. Here is our generic polynomial. It's nth order. Any of the AA coefficients can be 0. Any of them can be negative. For us, they're all going to be real. But I mean, technically speaking, this also works for complex coefficient polynomials. But let's not worry too much about that. So what you're going to do, and I haven't even told you what the Routh-Hurwitz criterion is, but the very first step in applying that Routh-Hurwitz criterion is to build this what's called a Routh array. And the Routh array is simply a table, and there are as many rows of the table as there are coefficients in the polynomial. Okay, so an nth order polynomial will have n plus 1 rows in its Routh array. The next step is to populate the first 2 rows of the Routh array. You take your highest order coefficient, and it goes here in the top left. And then the second highest coefficient goes here in the second row, first column. And then you keep populating this in what I like to call a serpentine fashion. So top, then down, then over and up, then down, then over and up, then down, then over and up, then down, then over and up and down, dot, 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 until you run out of coefficients. Okay. So after we line out how to fill this array, I will give you plenty of examples of how to do this. The next step is to fill in the rest of the array. Let's see if I can go back to here. There we go. So what you're going to do is you're going to eventually fill in the rest of the rows of this array, and then you're going to have these zeros that end up pop out over here. Sajad, question?
Yeah, you said that the number of rows is equals to the number of coefficients, does that mean like if the coefficient for s to the n minus 3 was 0, you wouldn't put it in there?
No, that was an oversimplification on my part. The true statement is, for an nth order polynomial, you will have n plus 1 rows, regardless of the exact value of the coefficients. And I think it's important to see that if your coefficient is 0, it still gets entered in a 0 here. Is that clear?
Yes, thank you.
Yeah, sure. Yeah, so if a sub n minus 3 were 0, as you suppose, then you wouldn't just skip this. You would write this as a 0. And then you would continue on. When you run out of coefficients, when you get to the last coefficient, you are free to keep going with zeros until you get tired of drawing zeros. And that sounds kind of silly, but if you have an even order polynomial, then your a0 will actually end up here, and that means that your coefficient here needs to be 0. Okay, so but we'll see examples of that in a moment. Okay, so in the following slides, I'm going to teach you how to calculate these B's and the C's and the D's all the way down to the bottom. They all follow a pattern. The pattern is strange, but there is a pattern. To calculate the lower rows, you're going to do what's called take the reverse determinant of the upper rows. I think that I will recreate that Routh array here just for the time being. So this is a sub n minus 1, a sub n minus 2, a sub n minus 3, etc. So to get this coefficient, which I'm calling b sub n minus 1, what you want to do is you want to take the determinant of these coefficients. So the left-hand column and the second to the left-hand column. So that's this determinant right here. And then just to confuse you, there has to be a negative sign hanging outside all of these determinants. And then the normalization factor for all of the B row entries is this value right here, a sub n minus 1. So let me change colors. If you want to calculate this, which I'm calling b sub n minus 3, then you take the determinant of this column and that column. Yeah, so all of these determinants in their left-hand column take the left-hand column of the rows above. So this is the same as that. Now what changes as you go from left to right in the B row is this column. This column increments left, oh sorry, increments right with the B's. Okay, so if you were to calculate this value, then you would take the determinant, so this would be b sub n minus 5. This would be the determinant of a sub n minus 1, and then the next a coefficients, a sub n minus 6, and a sub n minus 7. You would then normalize by that same value, a sub n minus 1. Okay. So let's talk about how to go to the next row. So this would be the C row. And to find the C entries, you're going to do the exact same procedure where instead of the top 2 rows, you're just going to look at the 2 rows above your C row. So to get C sub n minus 1, I want to take the determinant of these 4 numbers, a n minus 1, b n minus 1, a n minus 3, b n minus 3, and I want to normalize by the leftmost entry in the B row. Okay. So check your recognition of this pattern and see if you can write an expression for c sub n minus 3. I'll wait a second and see. I'll give you a chance to think about this formula. So it's going to be a negative determinant. I don't know if I give myself enough room there, but we'll see. And the left-hand column is going to be the same as this. So that's a sub n minus 1, b sub n minus 1. And I certainly didn't leave myself enough room. The next two are going to come from here. So this is going to be a sub n minus 5 and b sub n minus 5. And we're going to normalize by the same entry, the leftmost entry in the b row, b sub n minus 1. There was a question, does stability always describe poles in the left half plane, or is it based on the closed loop transfer function? So let's take a second and consider, what does it mean to be a pole? It means to be a root of the denominator of the closed loop transfer function. So I think the answer is it's not an either or proposition. You have to find the poles by looking at the roots of the closed loop, of the denominator of the closed loop transfer function. And if those roots are in the left half plane, then the closed loop system is stable. This is the pattern or the algorithm for building the Routh array. Are there any questions on this pattern? And this pattern continues until you get down to the last row.
Yeah, I had a quick question about
Sure.
the pattern actually. So you were saying in the previous slide that when you're initially populating the A rows, you do so until you're out of coefficient terms. Is that correct?
Yeah.
So because when you're calculating the B rows, they're based on, like, say, B n minus 3 is based on an A n minus 5 coefficient, which is, I guess, 2 up from that. And then the C row is based on, will you always have, if you have an A n minus 5, are you guaranteed like a B n minus 5 as well?
No, actually. So let's go back here. So let's say we've got an minus 1, an minus 2, an minus 3. And let's say we've got, that's it. Let's say that's it, and we've got zeros forever onwards. So the bn minus 1, that's going to be some number, yeah? It's going to be the determinant of the a's that I've written down here. But what happens to bn minus 3?
Well,
go ahead.
Yeah, it doesn't have the, it doesn't have an an minus 5. It has 0 as that term.
Exactly. So b, in this case, bn minus 3 is going to be the determinant of an minus 1, and zeros. And I think you guys learned, I hope you learned in your linear algebra class, is that a determinant with all zeros in one of the columns, that's a 0.
0, yeah.
Yeah. So the pattern that will end up emerging is that this array will be, by and large, what's called upper left triangular, basically. Yeah. Exactly. You're going to get zeros that end up creeping in. And so there, I guess what I'm trying to say is that none of the rows will be any longer than the A rows.
Right. Okay.
Cool. That's a great question.
Is there no such thing as like bn minus 2 or any even number for the B's and C's and so on?
Correct. Yeah. Since we're just doing one row per letter, there is no B. There's no n sub n. There's no sub n minus 2s or n minus 4s. Again, the numbering, you're going to see, if you look this up in different textbooks, you're going to see different numbering down here. I like this numbering because it means that these two, like everything in a column after the first row, has the same subscript, and that kind of pleases me. But I've also seen this with different numbering, where this is actually B sub 1, and this is B sub 2. So don't be thrown off if you read a textbook that has different numbering notation. The subscripts on the B's, the C's, and whatever, that has no technical bearing on anything.
Okay, thank you.
Yeah. Okay, so what can we do in 2 minutes? I think we can do our very first example. And this is where we say, the state, the Routh-Hurwitz Stability Criterion, is once you've built the Routh array, the way to determine the number of poles in the right half plane is by the number of sign changes in the leftmost column of the Routh array. Okay, let's, I'm going to run through this example quick, and I'll probably have to redo it on Monday, but let's give it a go. So step 1, build the Routh array. Step 1a, determine how many rows that array is going to have. So this is starts at the 3, s to the 2, s to the 1, s to the 0. So this is a 4-row array. And this looks like there's your leading coefficient, there's your second leading coefficient, there's your next coefficient, and there's your last coefficient. And then if it helps, you can keep drawing zeros until the cows come home. This entry is going to be the reverse determinant. So determinants 2 by 2 are usually upper left times bottom right minus the other diagonal. But if we're doing the reverse, the negative of the determinant, it's actually the opposite. It's the lower left times upper right minus 1 times 6. So this is 60 over 6, looks like 10. And as Elliot was just asking, this is the determinant 1600, which is 0. And then when we get zeros, we can actually stop, because what's going to happen? We get a whole bunch more zeros. Yeah. So let's go to the C sub 2. That would be 10 times 6 minus 0 divided by 10. So I think that's 60 minus 0 divided by 10, so we get back to 6. All right. So we have, this is the completed Routh array. So before I mark it up, this is what's called the Routh array, and we use the Routh array to apply the Routh-Hurwitz criterion. And this criterion is look at the leftmost column and then check, are there any sign changes, SIGN changes? So this is positive, this is positive, this is positive, this is positive. There are no changes, so 0 changes implies 0 right half plane roots. So that's the way to use the Routh-Hurwitz criterion once you've built the Routh array. It's a little bit anticlimactic, right? It's usually pretty laborious to build the Routh array, especially for higher order polynomials. But then you just look in the left-hand column and ask, does anything become negative, basically? There should be, is there a 10 or 11? Okay, I guess I went too quick here. So this entry, which I'm going to call B sub 2, is the determinant of 16116 negative over 6. And so this looks like negative of 6 minus 66 divided by 6, which is 60 over 6, which is 10. Now I may have screwed that up again, but I think, did you follow that arithmetic? Yeah, okay, sweet. Okay, we will see lots more examples in the next class. In particular, we will see the actual real use case for Routh-Hurwitz, which is what happens when, say, this is a variable. Okay, so stay tuned for that. We'll talk on Monday. Thanks, everyone.